Today I would like to discuss homomorphisms of modules, which mimics the definition of linear operators on vector spaces. And in general, the idea behind the word homomorphism is that it is a certain map that preserves our chosen structure. So definition for V and W to our modules. Phi from V to W is a homomorphism if it is compatible with the module structure. More precisely, which structures do I have? So first, addition. So for every U and V elements of the module V, phi of U plus V should be equal to phi of U plus phi of V. And second, multiplication by a scalar. So for every element R in the ring, for every element V of V, phi of R times V should be equal to R times the image of the element V in W. And here we multiply using the module structure on W. And before I continue, there is an observation that if phi is a homomorphism, of modules, then phi of 0 lends to 0. For the proof, I employ a similar trick that you could remember from algebra 1. So we take phi of 0 and write it as phi of 0 plus 0. Then I use the fact that phi is a homomorphism, so I get phi of 0 plus phi of 0. And by subtracting phi of 0 from both sides, using that using that W is an additive group, so we have additive inverses, we get that 0 is equal to phi of 0, which is what we wanted to show. Examples. So, knowing me for more than a month now, you won't be surprised to see that I present the 0 example. So, 0, the 0 map is always a homomorphism, and it sends every element V to 0. And it is called the 0 homomorphism. And as usual with defining homomorphisms of between any types of objects, like abelian groups or groups or rings, vector spaces, the identity map better be a homomorphism. It is the identity homomorphism that sends every element P to itself. And then you can see that additivity and multiplication by scalar, these properties hold trivially. Then linear transformations are homomorphisms. And example / proposition. If P phi and psi from V to W are two homomorphisms of modules, then phi plus psi from V to W that takes V to the sum of phi V and psi V is a homomorphism. The proof of this proposition is a straightforward check of axioms, and let me start writing it in this corner. So first I want to check additivity. So I want to check that phi plus psi of V plus W is equal to phi plus psi of V plus phi plus psi applied to W. So let me write out the left-hand side. By this definition, phi plus psi of this sum is equal to phi of this sum plus psi of this sum. Now I use the fact that phi and psi are both homomorphisms, so I use additivity of phi and psi separately, and I get that the left-hand side is equal to phi of V plus phi of W plus psi of V plus psi of W. And now, by rearranging the summands, I can get that this is equal to the right-hand side, because if I get phi of V plus psi of V, this, by definition, is phi plus psi of V, this summand of the right-hand side. And similarly, the remaining blue summands give phi plus psi applied to W. And I continue proving that phi plus psi as a homomorphism preserves the structure of multiplying by scalars. So I want to show that phi plus psi of our v is equal to r times phi plus psi v. So the left-hand side is equal to, by definition, to phi of rv plus psi of rv. And this is equal to, by the second property of homomorphisms, that this is equal to r times phi of v plus r times psi of v. And now I can factor r out of this sum. And I get exactly the expression that is equal to phi plus psi applied to v in the parentheses. So this is equal to the right-hand side as desired. So we checked the definition of a homomorphism, and thus we can conclude that phi plus psi defines a homomorphism. As a corollary, we get that the set of homomorphisms which I denote by hom sub r from V to W forms an abelian group. Under this operation of addition. But we can observe something more than that. So example / proposition. If we have a homomorphism phi from V to W, and let's say that R is an element of our ring R, then R times phi from V to W, that sends V to R times phi of V, is a homomorphism. And for the proof, I again show additivity. So I want to apply R phi to a sum V plus W, and by definition it is equal to R times the result of applying phi to the sum. By additivity of phi, because phi is a homomorphism, we get that it is equal to R times phi of V plus phi of W. And now I can open the brackets and I get that R times phi of V plus R times phi of W. And again, by the definition of this path, we get that this is R times phi of V is the result of applying R phi to V, and similarly with the second summand. And multiplication by scalars. I would like to avoid writing out long lines of equalities, so I will just write what we want to show. And it is that for every S in R and every V in V, R phi applied to SP is equal to S times the result of application of R phi to V. So to sum up, another example slash theorem is that if we have a commutative ring R, and two R modules V and W, then the set of homomorphisms from V to W, which I denoted by hom sub R, from V to W, it has a natural structure of an R module. And an important remark is that the proof of this result uses that R is a commutative ring. So this is not true for general non-commutative rings. For the proof of this theorem, we will have to recall the definition of an R module. So we know that we already have the necessary operations, have the operations of addition from this proposition and multiplication by scalars from this proposition here. And what is left is that we want to check axioms. So we thus need to check the defining axioms, defining properties of the module. So we want that for every pair of elements, phi and psi, of this set, and for every pair of scalars from the ring, we first have distributivity. Should be equal to R phi plus R psi. Then distributivity on the other side, R plus S times phi, should be equal to R phi plus S phi. And third, we need to check associativity. So R times S phi should be equal to RS times phi. Writing out these checks is very similar to writing out the checks that we wrote in the proof of this proposition. So let me, for example, show one. So R times phi plus psi applied to V. This is equal to, by this definition, to R times phi plus psi applied to V. Then we use the definition of addition, and we get R times phi V plus psi V. And by distributivity, we get R times phi V plus R times psi V. And now we use the definition of scaling homomorphisms again. So we get R phi of V plus R psi of V. And I would like to omit checking numbers 2 and 3, because you're probably already tired of seeing very similar strings of equalities being written out. So I will consider this theorem proved. And I just realized that I want to be more clear about why this, where the proof of this theorem breaks. And it breaks in the place where I omitted the check that R phi is a homomorphism. So I want to check that R phi is multiplicative. So I want to see that R phi applied to SV is equal to S times R phi of V. So by definition of this homomorphism, down here we have R times phi of SV. And this is equal to R times S times phi of V, because phi is a homomorphism. And right here, I'm going to use that R and S commute. So I would get S times R times P of V. And finally, I use again that this definition, so I get S times R phi of V. So the problem is right here, where I want to exchange R and S like this. So this is not true for non-commutative rings, because this proposition does not hold for non-commutative rings.